Imagine the darkest thing in the universe. A black hole, a cosmic trap from which nothing escapes. For decades, we thought black holes were defined by their perfect darkness. But what if I told you that scientists have created a version of a black hole in a lab, and made it glow? This isn't about building a real black hole, but about simulating its essential features in a controlled environment. Using clever tools, physicists recreated a model that behaves like a black hole, coaxing a faint glimmer of light from the simulated edge of darkness. This glow isn't just a trick. It confirms a prediction by one of the greatest minds in physics. The journey to this moment unites our curiosity about the stars with the strange rules of quantum mechanics. This laboratory breakthrough could help unite gravity and quantum physics into one grand theory. So, how did they do it? To find out, we'll travel from the edge of space and time to a lab in Amsterdam, where a simple chain of atoms revealed a cosmic secret. To understand the experiment, we need to know what a black hole is. Imagine a massive star running out of fuel. Its gravity wins, collapsing it into a point of infinite density, a singularity. The gravity here is so strong, not even light can escape. Picture a bowling ball on a trampoline, but with the mass of a mountain. The dip is so deep, nothing can climb out. That's a black hole, a region where gravity rules absolutely, and light itself is trapped. We can't see black holes directly, but we detect their presence by the way they affect nearby stars and matter. They are the ultimate cosmic voids, warping space and time to their limits. Black holes are fascinating because they push our theories to the breaking point. They're the edge of our knowledge, a place where physics as we know it unravels. And now, scientists are learning to recreate this edge in the safety of their labs. By simulating black holes, we can probe mysteries that were once out of reach. Let's look closer at the defining feature of a black hole, the event horizon. Every black hole has a boundary, the event horizon, a point of no return. It's not a physical surface, but a one-way door. Once crossed, nothing escapes, not even light. Imagine paddling a canoe toward a waterfall. There's a point where the current is too strong to paddle back. That's the event horizon. It hides the singularity from the universe, cutting off all information from within. We call it an event horizon because no events beyond it can ever be seen. What happens inside, we don't know. No information escapes. This one-way nature is what scientists wanted to simulate in the lab. They didn't need crushing gravity, just a boundary where waves or ripples could enter, but not leave. By building an artificial point of no return, they could study the strange physics predicted at this edge. The event horizon is where the known meets the unknown. And it's here that a great scientific mystery was waiting to be solved. Next, let's see how you build such a boundary on a tabletop. How do you create a black hole in the lab? How do you build an event horizon in a lab? Not by crushing stars, but by using analog systems. Different physical setups that follow the same math as black holes. It's like using a wave tank to study tsunamis. Not the real thing, but the same rules apply. For black holes, the trick is to create a situation where something moves faster than waves can travel through it. Imagine sound waves in water. If the water flows faster than sound, any sound downstream can't travel back. An acoustic event horizon. Scientists have used supercooled fluids and optical fibers to create these analogs, trapping sound or light in one direction. The goal isn't a perfect replica, but to capture the essential ingredient, the event horizon. By creating a one-way membrane, scientists can test if the strange quantum effects predicted at a black hole's edge actually happen. Each analog system is a piece of the puzzle, letting us test theories impossible to verify with real black holes. The Amsterdam team set out to do just that. Simulate an event horizon and see what happens. Here's how they did it. At the University of Amsterdam, scientists built a universe out of a one-dimensional chain of atoms, like beads on a string. They controlled how easily electrons could hop from atom to atom, creating a gradient, easy at one end, harder at the other. At a certain point, hopping backward became impossible, a one-way street for quantum information, a tabletop event horizon. This setup was inherently quantum, letting them study effects where gravity and quantum mechanics meet. With their miniature event horizon in place, the team watched for a faint signal predicted by theory. According to Stephen Hawking, event horizons aren't perfectly black. They should glow with a special kind of radiation. The chain of atoms heated up, but not uniformly. The temperature rose in a way that suggested a glow from the simulated event horizon. For the first time, they observed the analog of Hawking radiation. This was a breakthrough, a lab-made black hole that glowed just as theory predicted. But what is this mysterious glow? Let's explore Hawking radiation. Why should the edge of a black hole glow? The answer lies in quantum mechanics. Even empty space is a sea of activity, with virtual particles popping in and out of existence. Near an event horizon, a pair of virtual particles can appear. One falls in, the other escapes. The escaping particle becomes real, making it look like the black hole is emitting radiation. This is Hawking radiation, a steady stream of particles that slowly drains energy from the black hole. For stellar mass black holes, this process is incredibly slow, but for small ones, it could be much faster. Hawking's idea was revolutionary. Black holes aren't eternal. They evaporate. In the Amsterdam experiment, the glow was the thermal equivalent of this process. Ripples in the atomic chain mimicked virtual particles. Some were trapped, others escaped, creating a thermal signature. They had seen the ghostly whisper Hawking predicted nearly 50 years ago. But how did Hawking come up with this idea? Let's look at the origins of this daring prediction. In 1974, Stephen Hawking made a startling prediction. Black holes aren't completely black. They radiate energy and have a temperature. This was the first time anyone blended Einstein's relativity with quantum mechanics. At a black hole's event horizon, immense gravity meets quantum effects. A perfect storm. Hawking's theory was beautiful but nearly impossible to test. The radiation from real black holes is far too faint to detect. For decades, Hawking radiation remained a brilliant but untested idea. That's what makes the Amsterdam experiment so important. While not a direct observation of a real black hole, it shows that Hawking's principles are sound. When you create an event horizon, even a simulated one, it radiates, just as Hawking predicted. This gives physicists confidence and a new way to explore the consequences of his idea. Uniting gravity and quantum mechanics is the biggest challenge in physics. The search for a theory of everything. Relativity explains the big stuff. Quantum mechanics, the small. But together, they clash. The lab-made black hole bridges these worlds, letting us observe their interaction directly. In Amsterdam, the gradient mimicked gravity. The atomic chain was quantum. The observed Hawking radiation was a quantum effect in a gravity-like system. One deep puzzle is the information paradox. Quantum mechanics says information can't be lost, but black holes seem to erase it. Lab simulations let scientists throw information into their black hole and watch what happens to the outgoing radiation. Does the radiation carry information out, or is it lost? Now we can get real data, not just theory. This tabletop cosmos could help solve one of science's greatest paradoxes. It may guide us toward a true quantum theory of gravity. This experiment opens a new chapter in black hole research. With a working model, scientists can tweak parameters and explore new questions, like simulating spinning black holes, or testing the information paradox. By creating more complex quantum systems, we might finally see if information is preserved in the glow from a black hole. Beyond black holes, this technology lets us simulate other cosmic phenomena, maybe even the Big Bang or wormholes. The glow from Amsterdam's atomic chain is more than a curiosity. It's a symbol of human ingenuity. It shows that the universe follows rules we can understand, and even recreate. We stand at the edge of a new era, building miniature universes and asking them questions directly. The cosmos is speaking, and for the first time we're learning how to speak back.